Hi everybody, let's do a review of algorithms and programming. Like my other videos that I do on review, this should take about an hour. But as this is a big topic, who knows? Maybe it will take longer, I don't know. But the idea is that we're going to try and cover what is one of the larger topics in this course. Now, kind of not really surprising given this is a course on computer science, that we have a lot of programming. But it's not just programming. And it's also to do with algorithms, as in the way code works, and basically it's kind of problem solving as well. So we're going to take a look at this unit, give it a little review, and hopefully cover all the topics which will come up in the exam. At the end of this video, I'm going to do a little quiz. I've got a little quiz sitting by, ready to go. It's an AP quiz. Now, we did do this during class in the year, but helped to review, and it should cover all the different topics. So let's start. These are the topics. Let's just jump into them. Now, there's a lot of them. As you see, there's quite a lot of topics here. We'll be going through each one and discussing them. So now, when it comes to the order of things, it's not going to be totally ordered. I will maybe talk about some things, come back to them, because they all do link a little bit. But the idea is that you're going to know, when you look at all these, you should know what each one means and what they're all about. If you don't, then really focus on that and replay these sections. I'll try and put chapters in the video so you can jump and skip around and remember stuff. All right. So, what are we doing when we're programming? What's the point of writing code? Well, it's to find specific solutions to generalizable problems. So, you have problems, you have things you want to do, or there's problems you want to solve, you want to make something. You're trying to solve these problems, but you're trying to generalize what that problem is. So, for example, if you're trying to find numbers where it's like something to the power or something else, and you want to write some code to do that, you're not going to just write code that makes a code that a function that raises something to the power of 2, and then you write another piece of code that raises something to the power of 3. No, you want to try and write code that raises a number to the power of another number, and it does it in a general way so that it's very useful, because you generalize the problem and you made a specific solution to that general problem. Right? Now, to do all this stuff, we have to obviously deal with data. And we're handling data, we're storing data in places. We need to organize it and use it, right? So it's kind of like juggling. At first, just get used to juggling one thing, and then catch from one hand to the other. Then you got 2, and try and get used to juggling 2, and then add more. That's the way to approach programming as well. Start with a variable, print it out, then get 2 variables and more, and data structures and other stuff. So this is the model of what a program looks like. Most computers or programs look like this. We have some kind of input and some kind of output. They look similar, but they're kind of different. Mouse, keyboard, touch screen, microphone, all that kind of stuff is input. The screen, the sounds, their output, right? We're pretty familiar with these because we use them all the time. But the computer, in between the input and the output, is doing stuff. And that stuff is what we're actually looking at with programming. You don't really have to be concerned about storage too much, other than you're storing some information. You need to save it, right? If I'm choosing a song to play, obviously I'm going to use a touch screen and input that choice. And then my computer is going to look up some kind of storage or store that file, look for where that file is on the computer. And then it's going to load it, and then somehow the processing is going to happen where it plays that music and sends the right signal to the speaker to make that song play. So we're really focusing here on the processing part, but you have to realize that all of these things interact together. The output, the input, these are all things that we have to handle in our programs. And so trying to work at them in separate ways is probably a good idea. For example, if you're building a piece of software, handle the inputs, respond to all the inputs in a separate way, deal with outputs maybe in a separate way. Save your variables at the start of your code and get all that data saved in a place, and then you can do your processing, right? And these things all move around between each other, but that's the general model. All right. So let's take a look at storage. Storage is the first thing. So the way when we're writing codes, we're storing stuff in variables, and variables is just a name for a piece of memory from the computer where we can save stuff. It's usually a fixed amount of bits somewhere in memory that we're given. And maybe if it's for example, if it's a number like 5, we'd be given, the memory would automatically assign probably 32 bits or 4 bytes of information, right? What am I saying? Yeah, about that. So yeah, like 4 bytes of information would be given to us, and we could save it, right? If the number gets bigger, then we're going to run into trouble. But generally speaking, the memory stuff is assigned. You don't really have to worry about how it does that. But usually we're using variables to save things. And it's like a container or a glass or some place you put things that can be changed. So I could say 5 into this variable, and then later on I can choose to overwrite that with a new value. So you're basically saving stuff in placeholders. Now, the name of the variable is important because we give variables names so that we can refer to them later in our code, right? So if you're trying to use this number 5, and I'm saving it in the variable num, then later on I can just go print num, and then it will print 5, right? So I can refer to that variable instead of referring to individual values. Why is it useful? Because variables, the name can stay the same, but the values can change. And it can be useful to do general things, right? We can print that number no matter what value it is. We don't have to always be printing that specific number, right? So it's like a way of generalizing. So variables can hold different stuff, especially in JavaScript. Variables can hold all kinds of things. You just type var, and then you get your variable. You can make it a string, like in the first one is a string, Bob. You can recognize it by the quotes. Booleans are variables which only really have 2 values. They have true or false. Integers are whole numbers, and floating points are numbers with a decimal place. And that's the different kind of types. We call this a variable type. Now, if you look at a string, if you imagine I'm making a string, and each letter is like, if you remember back to when we looked at how do we save letters, what is a letter? It's kind of like, remember we looked at ASCII characters and we said that each letter represented like 8 bits, and now we don't use ASCII, we use kind of Unicode, which is more bits. But just suffice to say, we're using a certain number of bits, but our text could be huge. So how much memory would that take? Who knows? Like, how big is your sentence? How big is the string? It could be a huge size of memory you need. So strings might be a little bit different to, for example, a number like an integer, where generally we get 32 bits. A Boolean doesn't even require 32 bits. To be true or false, really you only need 1 bit to indicate, is it true, is it false? That's it. So the memory requirements for these different variables might be different, and the computer is going to handle them in a different way. But again, this is really low level. Like, the kind of knowledge of like how many bits you're holding, it's not really part of this unit, but that's what's happening behind the scenes. Let's make a variable. Okay, so in JavaScript, make a variable using var just to tell JavaScript, hey, I'm going to make a variable. Here's the name of my variable. As long as this name isn't like some keyword that already exists in JavaScript, you're fine. But it generally has to start with a letter, but it can have numbers in it, as long as it's not the first one. So yeah, and then you make your variable semicolon, and that's it. And now you have a variable called name. All right. Now you can also do math and assign it to a variable. This notation, you'll notice here, is the way that CollegeBoard describes the equals. Like in JavaScript, we used equals. In CollegeBoard, they use the arrow. But here we're showing how we're adding 1 plus 2. This gets done first. So all the stuff over here gets done. First, it adds up 1 and 2, we get 3. So we then save 3 into this variable called pow. Okay, so that's just the general way it works, all right? This gets solved first, then we save it into there. Now, we also can mention at this point, I won't go into too much detail, but lists are also variables. Lists are the type of variable that have many values. Lists are basically a series of values all tied together, and we can refer to them with the same name. So we use that same variable name, but we also use an index surrounded by square brackets, like down at the bottom here. We use that as an index to look up a value. So the value here is the index 0. It starts at 0 in JavaScript. It starts at 1 in CollegeBoard. But we can use the variable name and this index system to look up a value. Why is it useful? Well, it means that you can look up, you can save and you can look up a bunch of different values which are all related with an easy way. You can just change this number and then you get a different value in the list. So instead of having to remember what the variable name is for each one, like variable 1, variable 2, variable 3, you could process the same instruction with just by changing this number here, and you can apply it to all of these. So it becomes really useful for handling data, a large amount of data. We'll come back to those a little bit later, but here's an example of a list in JavaScript, right? So we made a list here, a bunch of values, and here's where we print it out. We print ln mylist, and that'll just print it out there. We can refer to the first value, print out the first value, so we were printing out this one here, so we get 2. Print out the second, the third value, which would be the index 2. So remember 0, 1, 2 index. So that would print out 6. And now how do we get the last value? Well, remember it starts at 0. So the length of this list is, what is it? 1, 2, 3, 4, 5, 6, 7. The length is 7. The last index would be 7 minus 1, right? 0, 1, 2, 3, 4, 5, 6. So that's why I use the length minus 1 here. And this dot length is basically like a built-in feature of lists. And we'll come to that a bit later, but using this, we can find the length of the list. So the length of the list here would give us 7, then minus 1. So this will get calculated first. We'd end up with 6 here, and then it would look up the index 6 for my list, which would give us 12, and that's printing out. Then it's printing out 12. So that's how that gets there. And then finally, we change the value, the index 4, right? So 0, 1, 2, 3, 4, we'd be changing this 10 to a 9. And as you see, when we print it out, changes there. So these are all the different things you can do with lists. Kind of useful because all the time, we're just still referring to my list, right? We don't have to remember many different variables. So the point of this is that lists are a way of abstracting, having an abstraction, a higher level of thinking. It allows us to handle complexity. Imagine if your list wasn't just like 7 items long, but it had like hundreds of items. It would be really complicated to go through all of those things with variables and print each one out one by one. So using a list, we can easily just go through them. So that's why we use them. All right, so we'll talk more later about lists. This was just sort of an intro because we're talking about variables. May as well talk about list variables, but we'll come back to those later. Okay, so we have talked about this. Usually you'll see this in CollegeBoard. This is in most programming languages when we are assigning something into a variable. So that's an example. Now you can also use that variable when you're saying, okay, this equals this. You can say the name of the variable. So what happens here? Like, how can a variable talk about itself? Well, this is remember, we're doing the right side before we send it into this saving over here. So we do this first, and so it looks up, hey, what's the value of fuzz right now, right? Before we've done this whole thing, what's the value of fuzz at the moment? add 1 to that value, and it works out what that value is, and then it updates fuzz with the new value. So this gets done first, then it saves, and now fuzz is updated. Right. So, yep. All right, so here's an example question. What's happening here? It's saving the number 1 into the variable start. And you'll notice this is a CollegeBoard question, so we're using the arrows. And there's no VARs at the front because that's JavaScript using VAR. This is just kind of what we call pseudocode or kind of CollegeBoard style code. It's a kind of a programming, it's not a real programming language, it's a kind of just a simplified version of a programming language. So yeah, we save 1 to start, we save 20 into end, we save 3 into current. Then we take the value of current and save that into start. So now start is not 1 anymore, it's 3, because current was 3. So that is changed into 3, that gets saved into start. And now current gets updated with whatever current is right now, which is 3 plus 1. 3 plus 1 is 4, and that current gets updated to 4. So display start, which is 3, and display current, which is 4. That gives us 3, 4. Let's take a look at string variables. String is a type, we've seen that before, holding text. So we refer to them as strings. Why string? Well, if you imagine like it's kind of like a bunch of characters which are held together by a piece of string, I guess you can think of it that way. It's kind of like these are a list of characters, really. Now, strings have built-in functions, and getting to know a couple of built-in functions will be really helpful because, you know, sometimes we want to do stuff with strings, like we want to find the first letter, or we want to find the last 2 letters, or we want to check out how long is the string, or something like that. Do we want to make the first letter into a capital letter? These kind of things are common things that we might want to do with a string. Therefore, usually the language will give us some tools, some built-in tools to deal with those things. And so when you're learning a programming language, you're kind of learning some of these tools which are commonly used. And I guess like coders just get to know more and more built-in tools so that they can go and create their own code and use those tools. So we always used to say in coding, like my coding teacher would say, don't reinvent the wheel, right? The wheel exists, use it. You don't need to reinvent it, make your own. And so in a way, we're just trying to use tools that are already there and learn about what kind of tools we have. So there's a bunch of tools that we have for strings, but you don't have to really remember that many of them for this course, but there's a few which might be helpful. So now, we can access strings using kind of like this list style with using indexes. Not really that necessary, but it's good to keep in mind that, yeah, you could do it 0, 1, 2. It's kind of similar format. Starts at 0, the index. You could kind of do that, but yeah, there's other ways to do it as well. Whoa, so I was talking about built-in string methods. Now, you don't have to know all of these, okay? I'll put it out there. You don't have to know these. So it's not a memory thing. I mean, eventually you just use them enough that you remember what they are. In many languages, they're kind of similar, right? These kind of things are common things that you want to do. Like, you're always using programs that are using text. How do you think that they're displaying that text and using that text and searching that text and doing all those things? They're all strings inside your phone or your computer, and they're being manipulated and changed using these kind of functions. So behind the scenes, the code that you use every day is using these kind of functions to do stuff with the text. So you have access to them. When you make a variable, like here, I make a variable like str, and I say, hi, my name is Bob. I can use some of these variables by using this little dot notation. And so what we say is we say the variable name, we use the dot, and then we can use one of these built-in methods. We call them methods or functions, where index of, and the job of index of is to return the index for this thing if it if it exists inside this string. So remember, my string is, hi, my name is Bob. Is name inside this string? And what would be the result? The job of this method is to return the index of name if it exists inside string. If it doesn't exist, it's going to return -1. So what am I going to get? Well, you can probably see here if you read, it would return 6. Why? Because 0, 1, 2, remember the space is also a kind of a character. So 2, 3, 4, 5, 6. See, this name appears at position 6. So that's what index of would give me. Substring. Substring's job is to take a part of a string with a starting index and an ending index. And so that would return hi m. Okay, but it doesn't include this last one. It's up to here, not including. So it's not inclusive of this last one. So it would give me 0, 1, 2, 3, or 0, 1, 2, 3, right? So using this, we can get part of a string. I could change these numbers and it would give me different results. This one would change the whole string to be uppercase. And this one would change it to lowercase. Yeah. So there's all different kind of things you can do. And there's a bunch of other stuff which you can do too. Quite useful if you need to. Yeah. So that's those are string methods. You play with them, you get better at them, you practice them, you practice using them. And sometimes you have to look up the docs to figure out how they work. But it's fairly easy to look up the documentation and work out what are the inputs, what are the outputs, and you can do it. And so that's where your power comes as a programmer. Do you have access to these tools? Do you know how they work? And yeah, and so I hope that you're getting good practice of those. Let's move on to selection and iteration. Okay, these are some kind of coding structures. So now we've got some tools, we've got some variables. Let's do things with them. Code wouldn't be much useful if we just had variables. We need to do stuff and make choices. Really, it's like coming down to the choices that we're making. If the user clicks on this, then do that. So I'm writing this kind of code. You can hear it in the words I chose. If, right? If this happens, do this. So these are examples of choices. So we need conditions. Conditions that are either true or false. And if they're true, we'll do this. If it's false, we might do that. This is a kind of a binary choice where we have some test we're going to do and some actions will take place. So that's the point of a kind of a selection statement. These are selection statements where we're selecting one or the other. To do a test, and we'll look at the condition here, we need to set up a kind of a test where something would be true or false. To do that, we use these kind of operators, which would be known as condition operators. And these conditional operators are very similar to the ones you use in math, where we test, is x greater than 5, true or false? Is y less than equal to 6? Now, in this case, x and y are just variables in my code, right? These are just variables that I might have made. Name is a variable. These are all variables here, right? But I'm going to be testing, at the moment, is that age greater than equal to 18? If true, then do this. If false, do that. So we use all these different conditions to test things out. There's only two possibilities. It's either true or it's false. Now, when we get complicated, we can join these tests together. And it's possible to even like do more than one test. And yeah, we might be able to test multiple things out at one time. And in that case, you know, like we can join them together with AND. In the case of AND, both sides need to be true for the whole thing to come out to be true, right? So if you look at the example there, 4 less than 6, that's true. 5 less than 8, that's true. So both sides here are true. Therefore, the result will be true. However, if you look at the next one, this is true, yeah, but that is not true. 5 is not greater than 8. So this is false. Therefore, this and this becomes false because they're not both true. Therefore, the whole thing evaluates to false. We'll see the examples of this soon, but that's kind of how we do it, right? So let's try the next one. Or. Or is a slightly different choice, a condition, where or only needs one side to be true for the whole thing to be true. So if this is true or this is true, the whole thing will be true. The only way it's going to be false is if both sides are false. So even though, now this is not, so even though this thing is false, this thing is true. So therefore the whole thing will evaluate to true. Okay, what are these kind of ands and or things that I'm showing you? It kind of comes back to some kind of logic that happens inside a computer. You may see this in an engineering course where it's actually about like we have simple choices we can make between logic gates. We won't necessarily cover these, but these do come from kind of engineering, these concepts. And so there's a bunch of different like kind of logic that can happen inside a computer with electronics. We don't really have to worry about that kind of stuff. Okay, we're not here to focus on that kind of hardware stuff. So that's why it's not in our course. We just focus on, as coders, we think or, right? Either the person is over 18 or they have their parent with them, then they can go and see this adult movie, okay, for example. All right, here's another one. It's called not. The symbol is the exclamation mark. If you put that before something, it's going to flip it into the opposite. So you can join nots together with other statements, like here, and you can see that not would flip whatever the result of this is. So let's look at this example. This is a question, and so let's look at this. It says, in a certain country, a person must be at least 16 years old, meaning 16 years old or over, to drive a car, and must be at least 18 years old to vote. The variable age represents the age of a person as an integer. Which of the following expressions evaluates true if the person is old enough to drive but not old enough to vote, and evaluates to false otherwise? So we're looking for people who are 16 and over but less than 18. All right, so let's evaluate each one. This will give me 16 and over, and this will give me less than or equal to 18. Notice there's an equal sign there. I don't want to include those who are 18. So for example, if the user here, the age is 18, this is going to be true, and that's going to be true, and the whole thing will be true. I guess that's not going to find the thing that I'm looking for, which is the person old enough to drive but not old enough to vote. That would give me a true, wouldn't it, for 18? And at 18, you are old enough to drive. So I don't want true, I want false for that. So no, that doesn't work. Let's look for this one. 16 and older, okay, and not 18 and older. Not 18 and older. So that might work, okay? Because let's say, for example, the user's 18. If they're 18, this will be true, but this will also be true here, but then that true becomes flipped by the not, so it becomes false, right? That's true, but the not turns it into a false, because not true equals false. So that becomes false, and therefore the whole thing is an and, it breaks, and it becomes false. But if I'm 17, this is false, but that not flips it into a true, and therefore it's true and true. So 2 does work. This, unfortunately, I don't think it will work, because less than 18, that might be true, but not age less than 16. Oh, hang on, wait, this might work. So this is kind of flipping them around. So imagine this is the less than 18 part. That's what we need. Someone is less than 18 because they're not old enough to vote. But what happens here? Now, if the person's 16, right? If the person's 16, this will be false. But that not will flip it to be true. So they're not only less than 18, but they're also greater than 16 or greater will get this to be true. If they're less than 16, this would be true. But that would be flipped to false. So then we'd have a false here. So I think 2 and 3 are the ones that work. All right, so let's look at how we put these conditions. So we're just studying here conditions to test, right? So the idea is that we get an if statement, right? The if and else statement is going to basically do this test. So that the condition comes in here, we test this condition. If it's true, we're going to do this thing. If it's false, then we're going to go and do this thing, right? So there's options for both, if they're true or they're false. And then we continue the code afterwards. Okay, let's look at an example. This example is using a let command. Now, let's not get into too much. Let, we haven't really covered much, but imagine that let says, it's another way of saying var, V-A-R. So let's imagine we made a variable number equals 2. Here, if the number is greater than 0, then we're going to do this. So that's an example of an if statement, right? And will it be true? Yeah, the number is 2. So that becomes true, right? 2 is greater than 0. So we would run code. In this case, number is minus 2, so this wouldn't be true. And therefore the code would not run. So it would skip that part and just continue going after that code. All right. Here is a question which I don't think we've covered mod yet. Probably shouldn't be talking about this one, so I'm going to skip that question. We haven't covered mod. Mod is an operation, an arithmetic operation, to find the remainder when you divide. So if I divide num by 1, what's the remainder? So we haven't covered this yet, so I probably won't do this yet. I think it's probably not a good idea. But maybe a quick reminder of mod. Yeah, actually, look, we've covered it. We've covered it before. So a reminder, remainder after division. So if I take that number, divide it by 2, what's the remainder? If that remainder is 0, then this is true, right? So that what's going up here should be one of these. It's meant to display odd if this condition, if num is odd. So if I divide num by 2, and I get a remainder of 1, that would give me that would be true for all odd numbers, right? Because if you divide any odd number by 2, the remainder will be 1. And so this D would be the right answer for that one. Here's a set of conditions for a video game, okay? And this says if the timer is less than 30, 500 bonus points. If the timer is between 30 and 60, then 1,000 bonus points are awarded. If timer is greater than 60, then 1,500 bonus points are awarded. You try and find the logic for these statements. There are 2 answers here. We're looking for the logic. Okay. Okay, so this says here that, let's check A. Bonus becomes 500 if timer is greater than or equal to 30, right? So you notice here, less than 30 is 500, but 30, between 30 and 60, we get 1,000. So it makes sense if it is greater than 30, we could add 500. That would take us to 1,000. And then we check and see, is timer greater than 60? Then we can add 500 more. If not, we'll just stay at 1,000, right? So that would work. This logic would work. This one does it the opposite way. Does it remove any? So this says, let's set it to 1,500. If the timer is greater than or equal to 30, then let's minus 500. Seem right? It's greater than or equal to 30. But this doesn't quite catch So let's say, for example, yes, it's greater than or equal to 30. Let's say it's 70, but we're still minusing 500, which doesn't match the bonus here, right? If it's greater than 60, we'd get 1500 bonus. But even if the value is 70, see here, greater than or equal to 30, 70 is greater than or equal to 30, it would minus the 500. So that's not correct. So not B. Here, if timer is greater than 60, do this, right? This one. If timer, so next condition, if timer is greater than 30, bonus would be 1000. Well, again, if the timer is, let's say the timer is 80, this is true. Bonus is set to 1500. But the next one would still run. It's not if and else. This is if. So this one would run next. And it would say, yep, 80 is greater than or equal to 30. So then it would set the bonus to 1000. And then it would say, check this one, and that wouldn't be true, but our bonus would be 1000 for a timer of 80. That doesn't match our conditions. So I already found it was A, it was true, and then D would be the other one. Timer is greater than 60, set it to 1500. It has the conditions here using AND, greater than 30, less than or equal to 60, and less than 30. So these are the exact conditions in here. All right, let's skip this because I'm gonna come with questions later. Okay, now let's talk about loops. Loops are ways of doing code many times, repeating some code over and over again. Just so happens that we don't have to write code out again and again and again, the same code. It's better to use a loop. So let's look at things that we might do to give loops. All right, so here's a loop of someone's day. I went to class 3 times, I ate lunch, I go to lab, go to class, go home. That's my day. But instead of writing go to class, go to class, go to class, I used a repeat loop. Now, obviously, in that example, I was going to the same class here, but very simple example. This is iteration, okay? So this word iteration is part of like what you have to do for your performance task, where you have to include an algorithm with iteration. So these mean either we're going to repeat something a certain number of times, or we're going to repeat something until some condition changes, like something is false or something is true. So we're going to keep going until something like so. These are the different kinds of loops that we can have. Either we know how many times we want to do it, or we don't. So, for example, you might want to practice free throws 50 times. You got 50 balls, you're going to hit those 50 balls. Okay, when you hear the bell, it rings a certain number of times. That's a repeating X times loop. But let's say you just keep eating until your dinner is gone. You don't know how many times you're going to chew or eat, but you just keep going until it's done, right? That's repeat until. So generally speaking, we use the for loop for repeat X times, and we use the while loop for an unknown amount of times. Here's an example of a for loop. We got 3 parts. We set up the conditions. So we set up a variable to do some kind of test. We do the test of that condition. If it's true, we do some action. We update the expression and we go back to the start, right? And usually this update is changing the counter or changing something in the expression. It's probably easy to show you, but the for loop has this structure. And this is where we set up a variable. This is where we do a test on that variable, and this is where we update the variable. Let's look at the example, right? Well, it wasn't a great example, but that's how it looks in code, and we'll look at some examples later. The while loop, it only has a condition, and it runs until the statement is false, until this condition, is false. So as long as this is true, it'll keep going and going and going, right? While the condition is true, do something. You have to decide what that condition is, and you have to make sure that the condition does change, and eventually it will end. Okay, don't get confused between equals and double equals. This is assigning a value. Saving, like if you're saving a value into a variable. This is comparing two things to see if they're equal. CollegeBoard uses this one instead. It uses equals to compare things. So it can get confusing. But in JavaScript, we're using these for different purposes. All right, here's a for loop. An example, and I use let again here, but usually we use var. So var I equals 0. This is the test that we're doing. So as long as if this is true, we'll do the loop. And this is how we're updating the variable after each loop. So each time we loop, we're adding 1. This means add 1 to I. And so as long as I is less than 10, we'll keep looping. In this case, we're using a variable here. Count is going to be 0. And the while loop, we'll just have one condition in here, just the test. Count less than 10, keep looping. And here's where we update the count to make sure that eventually we will get to be 10 and stop. So these are the different kind of structures that we've just learned. We've kind of seen that regular code goes like this. One thing, then the next thing, the next thing. That's regular code. But this kind of thing is a loop. And this kind of thing, this is iteration. This is selection, selecting one or the other. So iteration, sequencing, and selection, the three types of code that we've studied in this course. So in CollegeBoard, they use these kind of loops. They don't use for and while, they use for, but it's a little bit different. They use repeat until. So this is going to be false, but when it's true, it will stop. All right, until this is true. So therefore, we set x to 0, result 0, and we're going to stop when x is greater than 5. So add to result, add x to result, add 1 to x. Keep going, keep going, keep going. And then it says, what will be the results? What's the value of result after the code segment is executed? So first we start with result 0 and x is 0. And then we add 0 to 0 and save it in result. So result's still 0. And then we add 1. So we're adding 1. 1 gets added to result and gets saved. So now result is 1. We add 2. Right? And each time we do this, we're adding 1 more to result. Right? We're adding that number all the way up to x greater than 5. If x greater than 5, it won't work. So 1, 2, 3, 4, and 5 will get added. Right? So the answer should be 1 plus 2 plus 3 plus 4 plus 5. Okay, so that would be, well, I guess, is it 21? So that's that. Next one. Oh, what did I say? 21. That's 15. Sorry, 1 plus 2 plus 3 plus 4 plus 5. 21. 15. Okay, so this is a robot question. All right, so this is using some loops now to try and do something. Do something that we're trying to get done. We're trying to use repeats. These are repeat 2 times loops, or 4 times loops. This is a little easier to think about. Let's look at the code. Repeat 2 times, move forward. 1, 2, rotate right. Repeat 4 times. 1, 2, 3, 4. Rotate left. Repeat 2 times, move forward. 1, 2. Okay, so that's this code here. Now, let's see. So this is the goal is to get this robot into this gray square. When the robot reaches the gray square, it turns around and faces the bottom of the grid. Which of the following changes should be made to the code to move the robot back to its original position in the bottom left square of the grid and facing toward the bottom of the grid? So, will the same algorithm work? So we have to check. If we're going down here, which way do we have to turn? 1, 2. Do we rotate right or left? Well, rotate your head around if you really can't do this. but you actually will be rotating right. So no changes needed, I believe. 1, 2, 3, 4, rotate left, 1, 2, right? So it will move you back. Okay, we'll just skip that. So I've been through a few of these kind of questions. Here's an example of using some kind of methods, right? And now this is using lists and some methods in the lists. I think I should move this to after I talk about lists. So I'm going to talk about lists first, and then I'll talk about some of those example questions. All right, so let's come back to lists. We did look at these before. I said I'd come back. The idea is that you're pretty comfortable with them by now. All right. So in this example, let's have a look. We save a bunch of different lists. They have different values in them. You notice that we can save lists with different values. Could be words or strings, could be integers, could be floating point numbers. And so that's how we make arrays. I've shown you how to access them, right? You can't access something outside the end of the list, so be careful of that. Now, I showed you how to get the length of the list. We use .length to find the list. So in this case, scores.length would be 6. Okay, so that's built in. Now, how do we add a value to the list? Well, there is a way to add a value, and we can use the .push method. That's actually a built-in method to add something to a list. In CodeHS and in code.org, there are slightly different implementations of this. So there may be a different way. In fact, in code.org, I believe it's append item. And you have to use the method append item, the list name, and the value you want to add. So I believe it's a little bit different in code.org. In CodeHS that we were using, you can use push to add to the list. But it is possible. The point is, to add things to the lists, in most languages you can do it fairly easily. In some languages it's harder than others. But this was the result of adding. Okay. Interesting to note, you can actually have an empty list. You notice here that I made a new list with an empty list. That's possible. It's empty until I added 8 to it. So you can also remove things from a list by using the index. So use the name of your variable, .remove, and then in brackets, use the index that you're trying to remove. The difference, what's the difference between the square bracket and the round bracket? Well, these parentheses show you that remove is a method. It's a function, some kind of procedure that you're going to be using. The square brackets just indicate that something is a list that you're looking it up. You're either looking up an index. It's not a function. It's just part of the program, the programming language. All right. So this is how we would get rid of the fourth element, which is the H there, 0, 1, 2, 3, 4, and that's how we'd remove it. All right. How do we process a list? Like to go through and do something, the same thing to each value of the list. To do that, we can use a for loop, just like this. And we can use this condition, which is we set up a variable called I, set it to 0. I is going to be standing for the index. So if we want to access a whole list, we need to start at index 0, index 1, index 2, index 3, index 4, index 5. We want that index to be saved like as a variable. Makes things easier. So we make that index, we make sure that the condition is as long as I is less than scores.length, we can continue, because if we make it bigger, it's going to be outside our list. So, and then each loop we're going to add 1 to I. So starts at 0, increase by 1 each time. And we use that index to print out the value. So we look up scores using the square brackets and the index here. And so what you're seeing here is I'm printing index space and then the actual index number and then a colon and a space, which is this part, and then I print out the value. So I print scores and I, which gives me 85 here. And then next loop around, I is now 1, so I print 65 here. Right? Okay, so we've kind of covered for loop anatomy. I think you should be familiar with this now. You need to know how to do this. We've done it so many times. Just, yeah. It's 3 parts, not too hard. All right, let's keep going. Now, obviously here I'm printing out with print ln. If I was to not want to print ln, I might do just a print and then do I in a space. That's how I get the different result. So for loops and lists go together pretty well. Like for loops and lists are like peas in a pod. Like they really go together well. You use for loops to process lists, and that's how we can print out stuff, right? Very easily. You just need to do the same command for the whole list. And that's how you print. All right. If this list was 1,000,000 items long, the code would not change at all. You could still print out the same. All right. How do we go backwards? Well, you just change the for loop that you're using, right? So you remember that this I was standing for the index. This I is what we're using to go through the loop based on the index. So to go backwards, we start at the end, which is the length minus 1. That's the index of the length minus 1. Save that here as I. And as long as I is greater than or equal to 0, we just keep looping around and minus minus, right? Instead of plus plus, we minus minus. So it starts here, 0, 1, 2, 3, 4, 5. It starts at index 5. And then we get minus minus. Prints 4, prints 3, prints 2, prints 1, prints 0, and stops. Let's say we're trying to find a value in the list. Well, we need to combine then a for loop with an if statement so that we look at each number in our list and say, if that number is greater than 60, then let's print it. So this algorithm prints a number if it's greater than 60. So that's what we get, 85, 65, 88, 92 as the result. And these few, I will leave it to you. There's a few more examples here. We've done these before, so I will point out we have array functions here, which you can use. There's a bunch of them. This is part of programming languages, but for preparing for our test, we don't need that. And so I'm going to skip some of the functions here, and let's jump to sorting. Now, sorting just puts arrays into order. This is useful sometimes because it's helpful to have things in order. You can find them more easily. It's a major field in computer science to sort things, and there are many different ways to sort things. Some are more efficient than others. Efficiency and speed is a big factor in deciding how to sort something, but you can sort in JavaScript pretty easily by just typing sort. But yeah. Why are lists beneficial? Hopefully by now you realize why lists are useful. They help us hold a lot of data in a simple way, right? That's why it's a data abstraction. It allows us to do the same operation to a bunch of numbers. And so that's kind of like what you could do, right? You could say keeping the numeric values in a list makes it easier to apply the same computation to every data element. We can process that list with one instruction. Just like I showed you back here a little while ago, when I didn't need to do anything more. I could have a list of 1,000,000 items and I could just have this same operation over and over again. It's just going to do the same thing. So that's why lists are great. All right, now we're going to look at functions or procedures. Functions are just pieces of code that are reusable. And we can use them like a tool that we can pull out whenever we need to use them. And we can use them again and again and again. right? So we don't need to rewrite our code or have similar code. We just write functions that we can call whenever we need it. Functions are basically like we break problems down into solving one part. Like, so a problem that you have might have many different pieces, but we can write a function and hopefully it solves one piece of that. And then we can just run that function to run that solution many times. So the goal of your function design should be to make it clean and it does one job really well. This is known as procedural abstraction, right? Making a general solution to a complicated problem. Functions take inputs and outputs just like programs do. You use inputs, you use outputs. Functions also take parameters, which are the inputs, right? Parameters are separated by commas, and they're usually the inputs to a function where you can pass information in and it will do something with it.
Grade 6 Emily, please come to the sound.
A parameter is like the formal name for what you're expecting to get in the function. The arguments are the values that you're calling the function with. So when you give the function some specific values, they're known as the arguments. Often they're used interchangeably, but parameter stands for the formal like definition of the variables that you're giving as input, and the arguments are just the values that you're passing when you run the function. Return. So functions usually return a value. They can return a value, and when it runs something, it's going to do some action, and it can also send a number back so that a number will be given back at the end of that function, which you can then use in other places. And libraries are basically big collections of functions, right? Libraries are built into all programming languages, which use a bunch of functions. Like I showed you string functions, they're all in the string library. Libraries are just big collections of functions which we can use like tools. And we can import them and use them in our code. We don't have to rewrite the code. We don't have to invent the wheel again. We can just use those functions. So they're usually part of some library. Okay. All right, so let's look at a function. Example. This function has two parameters, a number and a direction. Here it says length and direction is the parameters, length and direction, and in this case the arguments given is 1 and right, 2 and down, 1 and left, 1 and right, 1 up, 1 left. It's saying which of the following represents the figure that is drawn by the program. All right, so this procedure draws a line length, this is the length, in that direction. So the cursor is then repositioned at the end of the line segment that was drawn. Okay. So let's see. The cursor starts in the upper left corner. The dots are spaced 1 unit apart. Okay, so we're starting up here. Draw one right. Okay, so it draws one right. All of them work. Okay, so that's the case for all of these. If we start here, they all have that. So we can't tell yet what's different. Draw two down. So now that we're here, draw two down. 1, 2. So this one doesn't work. No line there. This one works. That one works. That one doesn't work. So now we've got a 50-50. Draw one left. Okay, so draw one left. We're here. Okay, we're there. Good. Draw one right. Okay, back again. Draw one up. Draw one left. All right, so it seems like we're with B. All right, here we have a question about a substring, where we're taking a part of a string and making a new string. Concat will join two strings together, and length finds the length. So we assume that the string contains 4 characters. Okay, cool. A programmer is writing some code that's intended to remove the first two characters and the last two characters from old string and then assign the result to new string. So if an old string contains student, we remove st and we remove nt, and we should end up with ude. So the question is asking, how do you do that? All right. So I think let's answer this. So how could we do this? There should be two answers. Okay. So let's see if this is possible. Old string. Okay. So let's check A. This will give us a substring where we're taking the old string, which substring takes the old string, yeah, and 3, which is the starting index, and the length, -4. Okay, so the length of old string. Okay, -4. Why -4? Seems so weird. Length -4. Okay, and which basically it says remove length -4 from old string, starting at number 3. Okay, so that doesn't make a lot of sense to me right now. Like that kind of thing. I don't know. It seems a bit weird. I think what I'll do is I'll come back to this question another time. I'd rather just finish this a little faster. And I'm having trouble thinking I need to write it down. So I think that question is better when I can write it down to explain it. If a computer has fixed code, how does it generate random numbers? Okay, so random numbers are something you're going to come across. Random numbers are basically just ways of generating a number between a certain value and another value. They're quite interesting, but not that interesting. The details of how it generates random numbers is quite cool. But for your point of view, you just need to worry about random and between this number and that number. So this code here would generate a random number between 1 and 3. Okay, and so that's generally how it works. I'm going to skip this question too because we're running low on time. Here we are at simulations. Okay, now simulations, I haven't included many slides on this, but a simulation is basically a piece of code that is designed to copy some real life thing. Like, so we're trying to, like, for example, do an experiment where we can do a scientific experiment that might take a year to run in real life, but we can use a computer code to run it really quickly and test something out. And so what we're doing here, a simulation might be to, in this case, test out some scenarios. So we're going to see which is the least beneficial, right? So it's generally we're doing simulation for things that are really difficult to do in real life, not for things that we could just easily do in real life. Okay, so here an engineering company wants to test whether a change to car design will affect fuel efficiency. Well, that's great to do a simulation on because, I mean, if you have to redesign your car, build the car, then go and test it, well, that takes a lot of work. I mean, that involves a lot of extra work. So it's easier to do that in software than it is to do it in real life. An insurance company wants to study the effect of cold weather patterns on healthcare costs. Again, pretty good because these patterns and healthcare stuff, it's difficult to predict in real life and measure. A manufacturing company wants to determine whether using robots will increase productivity. Again, it could be pretty cool. Maybe it would increase productivity, maybe not. Okay, but again, building robots and putting them in the factory, then testing that out, would take a lot of work and cost. And you may, if you've already built the robots, then what are you doing a test for? And then a retail company wants to determine the most popular item that was sold on the website last month. That is not a simulation. That is something you can just look up and calculate very quickly. So it's not replacing some kind of manual work that would require a long time. That's just really looking up something in a database. So that would be D. That's not a beneficial thing. Okay, now when you write your code, you might write some code. It's going to sometimes run at a different speed depending on what you're doing. Let's say you have a list of 1,000 items, right? And you have a list and you're processing your list using a for loop, and you're going through each item. Now, if you're just going through one by one, then maybe your time it takes to go through that is just dependent upon how big that list is. As in, the time it takes you might be related to n. For example, like if n is the number of items in your list, it's going to take like 1,000 seconds to do that, right? 1,000 items, 1,000 seconds. Okay, fine. That's a linear equation. Just takes the amount of time. If you add some more items to your list, it's going to take a little bit more time. That's linear. Some x number multiplied by n. Now, if, on the other hand, in your list, you had to maybe check all of the other items in your list. So for each item, it was going to go and check, just see like, is that number bigger than other items in your list? So therefore, you're not only increasing the number of items that you have to check, but you're also increasing, like checking, you have to check that item multiplied by all the other items. That would be a polynomial problem. It's pretty reasonable. You can still work it out. It's going to take longer, but it's just going to be like more calculations, but you can still do it. And I'll get to log in a little bit later, but what if you had 2 to the power of n? So in this case, each item is going to have to do a complex thing for every single other item. And that would mean that your equation is going to increase exponentially, meaning that it's 2 to the power of however many items you have. Every time you add another item, you add another power. That's going to get really, really complicated. And so the more things you have, the more complicated it gets. Your program may not finish running in a reasonable amount of time. For example, it might take 1,000 years to finish the code. That we can say is an unreasonable amount of time. So in terms of efficiency of the code, there are different ways to do things, and they all have a different kind of speed at which we can do them, or different efficiency. Now, log might be an example where you have a list of n items, and you can do things by dividing the list in 2, and you can search divide by 2, divide by 2. So maybe in that case, you only have to search a quarter of the list, or a small fraction of the list. That's a very reasonable algorithm, a very fast and efficient algorithm to do, right? So we can sort of measure these things, and we call that algorithmic efficiency. For your point of view, you really just have to know the difference between these different ones, right? Logarithmic or linear. Polynomial is when you have any number here, and then it's raised to any power, right? So the number of items in your list raised to a certain power. So it's fine that even if of all the things in your list, you might still be doing a bunch of calculations on those things, but it's okay because it's still just a list with a bunch of stuff. If you were comparing every single item in the list to every single other item in the list, that would be more unreasonable territory. And so there's a difference between polynomial, where the power can be variable, but it's not related to the number of items. Whereas this one, the power is related to the number of items you're dealing with. All right, so here's an example of, I guess, I'm going to talk through an algorithm where we're trying to find a number in the list. So in this case, this is a search algorithm where we're searching for this ticket. Can we find this ticket in the list? Well, to find that ticket, you just keep searching, right? You search and you search and you search and you search and you keep looking through the list, and eventually you find the thing you're looking for. It's pretty dependable, but it's not super efficient, and not a really efficient way to find that number in the list. Eventually you'll get there, and on average you probably search half the list before you find it. The worst case scenario here is that you have to search all of the items and it's at the end. Or it's not, maybe if it's not even in the list, you've searched all the items and then you realize, oh, it's not there. Okay, so you've searched. That's the worst case scenario. Right? Here's an example of that. I searched the whole list. Oh, it's not there. So I've searched everything and I found it wasn't there. I had to check all of the items. That's a linear efficiency. Okay, if I have 100 tickets, I have to do 100 checks. So, algorithm 2 is binary search. Now this is a much more efficient algorithm. This requires our list to be sorted, but the idea behind this is that we're going to have an ordered list and we'll search in the middle of that list. If we search in the middle and we compare the numbers, we can see that if it's less than, we don't need to search the rest. So I'll skip the algorithm, but here's an example, right? Here's my list of tickets, and you notice that it's in order. Now, if I'm searching for 705 in this list, I check the middle. Go to the middle and check it. Now, it turns out that the one I'm looking for is bigger than 410. So I can ignore 117, 232, 245, everything to the left of 410 because I know that they're all smaller, right? And I'm looking for a number that's bigger. So therefore, I can ignore that. And I've already now divided my list in two. Now I can do it again over this side. So I, again, search the middle. And I realize, okay, I don't need to look to the right because the number I'm looking for is smaller than the number I'm comparing to. So I can look over here. And then I find my result. So in this case, this efficiency is much better than the linear one, right? This actually works out that you keep dividing, and it's kind of related to powers of 2. So we call this binary search because we're dividing by 2 each time. And so you'll see that when we plot this on the chart, it turns out to be this logarithmic graph. Pretty cool, because it just means that you don't have to do as many steps and your code will run faster. Okay, and so really this is related to the powers of 2. Okay, so much more efficient to do a binary search, but obviously you do have to have a sorted list to do that. That's the key. It has to be sorted, otherwise there would be no point. Like if this list that I did before wasn't sorted, then I couldn't logically conclude that if I don't find this, that I can exclude the left side. The only way I can exclude the left side is because I know they're all smaller, right? So it has to be a sorted list. That's the key. Okay. Now we're getting on time, so let me jump through this quicker. Which of the following lists can binary search be used for? Well, find the sorted list here. Which one is sorted? Now you see that the one on the bottom, this one here, it is kind of sorted because it's in reverse order. So even though it's reverse order, it's still in order, it's in some kind of order. This one is also in order, so I could use that one. This one is not. Wait, is it? Yes, it is. It's kind of in order. B, G, J, M, P. Right? So they're actually all in order, so I could use them all. Now, what can I do about the problems that are unreasonable? They're too complicated to solve. Or at least it's not that they're too complicated to solve, it's just that solving them would require more time than I have available, right? And in really unreasonable time. To solve these kind of problems, and these problems do occur, I mean, it's not like crazy kind of problems. These problems do occur, like for example on mapping, right? On trying to use mapping and figure out like which direction should I go. To calculate all the possibilities, for example, like you're trying to go from point A to point B. You're trying to drive, let's say you're trying to drive from your house to Kaohsiung. Okay, it's a long way. You could take so many different roads or go through so many different cities. Does your algorithm have a chance to does it want to calculate every single possibility? if I drove to Taichung, then I drove back to Taipei, then I drove to Hualien, then I drove back to Miaoli. Do I have to check that, really? I mean, it seems unreasonable to check it, but if they're all possibilities, then my algorithm would eventually check them. If I was trying to check every single possibility, it would be crazy to do that kind of thing. Crazy to check every single possibility. So in that case, I need a kind of a way to solve it where I'm not going to have these crazy ways, or like, I want to find something that's kind of efficient to search, that's not going to take a huge amount of time. So what we call these heuristics, where it's like a good enough kind of way to do it. This is an example. Like, there are many different paths to, if you want to visit all your friends' houses. So you're the green one, and you want to visit all your friends' houses. There's a bunch of different ways you can go, right, to visit them. So, but what do you need to know to do the best path to get to them? You need to know the distances, right? So if you knew that the distances were like these, then maybe you can make some choices, right, about which way to go. But if you have a lot of places to visit, how do you determine the best way to go? So this is where a heuristic is a good kind of it's a general way. I mean, you may not get the perfect solution. You may not be able to look at every single possibility and then figure out which is the best one. But you can say, oh, well, generally speaking, if I did a kind of like if I chose the smallest one available, like if I looked at the three closest ones and I chose that one, that might be the best way to do it. And so maybe you can see here, like, here's an example of how problems get crazy. If I have one house to visit, I know it's just one choice. If I have two houses to visit, there's two choices. But when I get to 10 houses to visit, it's 3.6 million choices. You can see this number is growing really crazily each time, right? So this problem needs a better heuristic, right? And to check the best path would require tons. And so to use a heuristic might be better, right? And so what we're trying to do here is optimize our way to do it, right? We can optimize the thing. And so we can use, instead of using an unreasonable amount of time, we can use a more efficient way, like a good enough way to do it. Like, so for example, when you're driving your car to Kaohsiung, maybe you think, oh, what's the closest major city to me? And is it going to bring me closer to Kaohsiung? Then let me choose that one. Okay, closest major city, Miaoli. Okay, I'm going to go there first. Next, do the same. Closest city that's close, going to bring me closer. Okay. Now, the closest city might be Hsinchu, but is it going to bring me closer? No. So I'm going to choose Taichung, and then again and again and again. And so maybe that's the heuristic you use. You don't have to check every single path. You can just figure out a simple way to do it, right? So algorithmic efficiency questions would look like this. And it might give you an example of where you've got a bunch of numbers of items, right? This is your n value. And this is the number of steps you got to take to calculate it. And you got to figure out, is this reasonable or unreasonable? Let's look at this. This is 10 times n. This is 20 times n. This is 30 times n. This is 40 times n. Is it really that unreasonable? No, it's not unreasonable. You can see that it's growing, yeah, but it's not growing in a crazy way. It's not like to the power of n. Okay, so we can say A, that it's reasonable. All right, we're coming up to the end here. We're almost there. So remember, this is a big unit, so it does take some time to get through. The limits of computing. Now, some problems just can't be solved. That's the facts. Some problems, you really just can't even solve them. There's not that many of them, but there are some problems which are just really impossible to solve. No matter how much time you give it, you wouldn't be able to solve it. So these are known as undecidable problems. Questions will try and confuse you, just like the question before. It can try to confuse you between reasonable, unreasonable, and undecidable. To really master these questions, you just have to know the difference between an unreasonable and an undecidable problem. Okay, undecidable problem means that no matter how much time, you can't solve it. Unreasonable means it's going to require a bucket load of time, but you can eventually get there. Okay, so some problems are unsolvable. Okay, and so we'll just leave it at that. Now, sequential parallel we covered in networking, so we're going to skip that, and I'm pretty sure that'll take us to the end. Yep, it does take us to the end. Okay, so I'm going to leave it there. I did say that I was going to cover some, and I'll just leave it with the dogs here. I did say I was going to cover some questions at the end, but I think there were enough questions in there that hopefully helped you out with the algorithms part. I don't think we need to go there. We've already done an hour and 20 minutes, so I'll leave it at that. I just hope that algorithms, now that we've done this, you're a little bit better at understanding what's involved. Please do check this list out and make sure that you really do understand these. Watch the chapter again and do some problems on them if you're not sure. And yeah, good luck. It's a big part of your course. It's 35% of the 70%. So it's a big part. 35% of 70% is like, what, 20 something? So it's a pretty big chunk of what you need to know, right? And so it's worth taking the time to understand all of these, not just the programming parts, but also these things at the end. Because I'm guaranteeing you that a couple of questions will come up about these topics at the end. So make sure you do understand them. We didn't spend as much time as I would have liked in class talking about them. So that's why this video is kind of being a supplement to help you understand them. All right, thanks, and I'll catch you next time.